Okay, next in line, C.1.4, find limits of rational functions that are undefined at a point. For example, find the limit as x approaches 2 of our friendly function here, x squared plus 2x minus 8, all divided by x minus 2, by factoring and canceling. So as we noticed before, we always want to try substitution. So we have our limit as x approaches 2 of our function. And I'm going to just go ahead and skip writing it because we can plainly see it right there. We have 2 squared plus 2 times 2 minus 8, all divided by 2 minus 2. All right, so when I make that substitution, I find that I get 0 divided by 0. And that's the indeterminate form. So I'll write it one more time. Indeterminate form. So what that means is that there's still possibly a limit. We don't know what or where. So we could substitute values really close to 2. We know that it's discontinuous. There's the function is not continuous there, but however there will be a limit because the function behavior should suggest that as you approach that value from the left and the right, that you're getting closer and closer to one specific value. And we know from the past, again, the first video, that this is 6. But we can find this algebraically. Again, the no calculator portion of the test is not going to allow you to graph it and see it so easily. So how do we deal with this? Well, what we can notice from here is that we have a quadratic function, and it looks like it might be able to be factored. So we will check it out. We'll say the limit, well, first of all, we'll just take a look at that x squared plus 2x minus 8. So factors of 8, that will allow us to add or subtract the middle terms to make a positive 2. And it seems like 4 and 2 will do the trick, so we need them to make a positive 2, so that's going to be a plus 4 and a minus 2. One hint that actually makes this factoring so much easier in calculus than algebra 2 is that you're going to try to go for a cancellation or finding the same term as the one in the denominator, because then that will create a 1, and then it'll just be x plus 4 times that 1, which is just left with x plus 4. So when you're factoring, one of the factors should be the denominator. So if it's not, it's either a special case or you did something wrong. So check it again. So now I can rewrite my limit as this. So now I know that x minus 2 divided by x minus 2 is 1, and 1 times x plus 4 is just x plus 4. So now my new limit is six. So I know that. And so later on when we get into continuity, this is called a removable discontinuity, meaning there's just a hole in the graph. There's one point in this graph where the denominator is 0 and the function does not exist. However, it's good for any other value of x. So it's called a removable discontinuity. And what questions are famous for on the AP exam is asking you, how can you redefine the function so that it's continuous everywhere? Well, one day when they say that, they'll just give you a function. We'll do an example one in a couple of slides here. When they say that, they're actually wanting you to find the limit as x approaches that number, and they want you to plug the hole up, basically. So think of it as, when you're finding this, you're finding what value will plug the hole. And that kind of makes it a little more visual. So we'll take a look at another example. We've got one here. The limit as x approaches 3 of x squared plus 5x minus 24 divided by x minus 3. So we will look at trying to factor our numerator. And if we do this correctly, I know this should be x minus 3. So a factor of 24 that has 3 in it, the other number has to be 8. And the 8 and the 3 have to make with addition or subtraction, a positive 5, so this has to be a positive 8. Okay? So I can rewrite my limit as x approaches 3 of x plus 8 times x minus 3 divided by x minus 3. Again, x minus 3 divided by x minus 3 is 1. 1 times x plus 8 is just x plus 8. So now my new limit, the limit as x approaches 3 of x plus 8 equals 3 plus 8, which is 11. So the function is not defined at 3, has a hole in the graph, and what that suggests though is that both the y values are approaching 11, and if you filled in the hole with 11, you would make the graph continuous. So that right there is the limit of the function. So moving on to here, we're kind of getting into and flirting with discontinuities. So some I didn't write the whole question out, but this is a multiple choice question on just a practice exam out of a book, and it said to describe the discontinuities of the given function. And there were, of course, the 5 choices, A through E. And one's a hole at x equals negative 3, a vertical asymptote at 3, holes at x equals negative 3 and positive 3. So how do you know if it's a hole or a vertical asymptote? Well, we kind of talked about that a little earlier, but notice there's no limit statement. But when it says describe the discontinuities, what they're actually asking for is what's going on at these certain values. And does the limit exist? Does it not? How can it exist? So on and so forth. So we notice that both the numerator and the denominator are both squared functions, both quadratics. So we want to factor both. And here's a case where we don't know what we're going to factor in the denominator. However, you should know your special rules from Algebra 2 and Pre-Calc, that when you have an x squared minus 9, that it's going to be plus 3 minus 3. So those were easy to figure out. In the numerator, I have x and x, and this makes it actually better, so the only factors of 3 are 3 and 1. And they need to add, so 3x and 1x need to add or subtract with each other to make negative 2. So I know that the 3 has to be the negative one, and then the 1 has to be positive. And just to check, negative 3 times the positive 1 is a negative 3. So that works out. So I'm going to rewrite my limit statement now. Or not my limit. I'm going to rewrite my function, and then I'll look at a limit. So I have x minus 3, x plus 1, all over. And I'm going to write the x minus 3 first, just to illustrate a point. 3. Okay. So I notice that I have a common factor, x minus 3, in the numerator and the denominator. If I were to plug the value, and here's where I would get my limit statement, the limit as x approaches 3, sorry for the delay, just want to write it legibly enough to read it. There we go. The limit as x approaches 3, if I substitute that, I'm going to get a 0 on the numerator and a 0 on the denominator, because it doesn't matter what the other one is as a number, because it's going to be multiplied by 0. So this will turn out to be 0. 0 times anything is 0. So I'm going to get the indeterminate form, 0 divided by 0. So I know that at 3, because 3 is the one that is the same factor in the numerator and the denominator, it's going to give me the indeterminate form. All right, this is going to equal 0 over 0. I know that is where the hole in the graph. Choppy sentence. Where my hole in the graph is. Okay, not a great sentence, but that's where the hole is. Okay, so the hole, where is it at? It's not at any it's not at 0. It's at 3. Because, and I didn't have to even go that far, because that the hole is where you have the same factor divided by the same factor. Okay, so, and we also know by now that any discontinuities in a graph happen where the denominator equals 0. Okay, so what else will make the denominator 0? Well, I know that a negative 3 will make the denominator 0, and I know if I plug a negative 3 in here, that will make my denominator 0, but my numerator will stay some number. So I will get some number over 0 if I plug in negative 3. Okay, so if I plug in negative 3, I get some number divided by 0, and that is going to be another kind of discontinuity where I have an asymptote. So called a jump asymptote. The graph, no, not a jump, I'm sorry. A vertical asymptote, and I'm thinking of an infinite discontinuity. So one side of the graph shoots off to positive infinity or negative infinity, and the other side of the graph will start again at coming down or up from either infinity or negative infinity. So basically, for this case, the graph will look something like this or something like this. All right. Whatever it is, but you know that there's going to be a vertical asymptote there because it's some number divided by 0. So it gets really, really, really huge as you get closer and closer and closer to the number. So this would be the, and I'm not going to rewrite the whole thing out, but the limit as x approaches negative 3 is going to be some number divided by 0. The limit does not exist, and that's where an asymptote happens. So if I was answering this question, my one answer here, C, says a hole at x equals 3, a vertical asymptote at x equals negative 3. So no limit question, no limit in the question, but I know that I'm actually kind of looking at the idea of a limit because I want to look at what's happening as I get to those numbers. So that's kind of decoding that and leading us into discontinuities a little later.